There's actually sort of a problem with vertical least squares. And the reason I called it vertical least squares is we're actually minimizing the error in a particular direction, right? Vertically, the y. So for example, that's not even rotation and variance. So if I get lines that are kind of horizontal, that works okay because, you know, the points. But if I got lines that are very steep, then as I move off the line a little bit, I end up with this huge error, which is not really right. I just moved off the line a little bit. And that's because I'm using this particular direction. And of course, it fails totally for vertical lines. So it's really not a good model. It's not a good noise model for what we're doing. So let's develop a slightly better model. We're going to refer to this as total least squares. And this you've also seen. So now what we want to do is we want to minimize the distance between the point, x, I, y, and some line, ax plus by equals d, where a and b are this unit normal, right? So it's actually the unit normal in the direction towards the line. So when you take the dot product of the point xi, yi, and ab, that would give you this here, okay? That should equal d, which is the distance of the point of the origin to the line. That's this distance here as is drawn there. And to the extent to which that point does not lie on that line, that perpendicular distance, as drawn here, is just ax plus by minus d, right? It's supposed to equal d, so if you subtract d, that's the dot product, and that's the perpendicular distance. At the end of the day, what that does is this gives us this new error function, e, pretty straightforward, and what we're going to do is we're going to minimize that error function now instead of our previous error function. How do we do that? Pretty straightforward. Same thing. We start with our e, all right? We're doing a minimization. We take the derivative with respect to the parameter d. That's the first one we're going to do. That generates this equation for us. We can use that to solve for d. And d is just this beautiful a x bar. X bar is the average of the x's plus b y bar. That's what these terms here are. Okay, so this now I've got an expression for d in terms of a and b. So I can substitute that back in, and I get this kind of ugly expression that we'll make beautiful in a minute. So I've now plugged these in, so there's no more d's in there. And look at that. That now looks very similar to the expression we had before, except now we've got this, these means subtracted. So if I stack up all my x's, x minus x bars here, and y's minus y bar there, and I'm actually going to call that matrix U, because I do, I can write this whole thing as UH transpose UH, where H now is this parameter AB. Remember, we got rid of D, we solved for D in terms of AB, and now we just have to solve for A and B. Okay, so now that we have an expression for E in terms of U, which are known from the x's and y's, and H, which is our parameter vector, in order to solve for H, what do? Same thing, we take the derivative of E with respect to H, repeat that equation, set that equal to 0, and that should start to look vaguely, annoyingly familiar, right? We have this matrix here, U transpose U, which is just made up of the x minus x bars stacked up, y minus y bars stacked up, transpose, etc., whatever, times my parameter equals 0. Remember what equations equal 0 are? Those were homogeneous equations. Aha. All right, so the solution to U transpose H equals 0, well, the dumb solution is set H equal to 0. We said that wasn't going to work. Remember when we did the essential matrix and when we did calibration and all that stuff? We said, no, since we have everything okay up to a scale factor, what we're going to do is we're going to set the magnitude of H equal to 1. Now, in this particular case, we were going to do that eventually anyway, because remember A and B, which is what H is here, were the components of the unit direction of that line. So A and B have to be a unit vector, so we might as well just set the magnitude of H equal to 1. And so you remember how you can solve that? You can do that whole SVD eigenvector thing again. So given U transpose U, you can find the eigenvector with the smallest eigenvalue, and that's your solution for H. I'm showing you this as a way of talking about that the right thing to do is perpendicular least squares. Here's how you do perpendicular least squares. And now the question that you really should be asking is, why is perpendicular least squares the right thing to do? Well, it's because we have in mind a particular model of noise.